Hello everyone and welcome to lecture 12. So this is the second part of the respiratory lecture. So in today's topic we'll be talking about gas exchange. So this is how oxygen is going to move from the alveoli into the capillaries and into the bloodstream, and then how it gets distributed to the tissues. And then of course the CO2 and how the CO2 is produced via metabolism in the tissue, and how that's moves into the bloodstream, and then at the level of the lungs moves from the blood and into the alveoli. So to start, we need to talk about the composition of air. Right, so we breathe in air. I spoke about it in broad terms in the previous lecture when I just talked about the whole air as a whole, and how it has a pressure of about 760 millimeters of mercury, and that's the total air pressure at sea level. But the air is made up of individual gases, right, that contribute to that overall pressure. So the primary composition really is about 79% nitrogen and about 21% oxygen. And now that percentage doesn't change regardless of the altitude. So even if the air pressure goes down, the percentage contributed by nitrogen and oxygen would stay the same. And I'll come back to that. You'll have a small amount of carbon dioxide, and the water content can vary depending on the water vapor in the air, how humid it is. There are some other minor gases like argon, neon, and helium, and so on that do contribute, but to a much smaller degree. So we'll primarily be focusing on nitrogen, oxygen, carbon dioxide, and water. So first, before I go any further, we have to talk about Dalton's law. All right. So this is the total atmospheric pressure. All right, is the sum of the contributions of the individual gases that I just spoke about. So I mentioned that at sea level, the atmospheric pressure is 760 millimeters of mercury. That's the same as saying 1 atmosphere. All right, so those are equivalent amounts here. So here again, here's 1 atmosphere. It's equal to 760 millimeters of mercury. And again, that's sea level pressure. If we go to higher altitudes, the pressure would decrease. Now, the components, the gases that make up the air, the individual gases, they contribute to the overall pressure. And they contribute depending on the quantity of the gas that's present. So for example, if 79% of the air is nitrogen, then the amount that it contributes to the overall or total pressure is 79%. So 79% of 760 is 597 millimeters of mercury. So it's related to the total quantity of that gas. The pressure that oxygen contributes to that atmospheric pressure is 21% approximately, and that's about 159 millimeters of mercury. And those are going to be the two main components, but then you have water, and depending on how much water is actually in the air, it can contribute, let's say if it's 0.5% here, it's contributing 3.7 millimeters of mercury, and then CO2 being very little in the atmosphere there, about 0.3 millimeters of mercury on average. All right, so you can see just the relative contributions from each of the individual gases based on their quantity in the atmosphere. And so what we call these individual pressures, or pressures exerted by the individual gases, we call them partial pressures. So we'll say the partial pressure of oxygen, that's what the PO2 stands for. It's the partial pressure of oxygen. And so that just is referring to the pressure in the atmosphere that's exerted by oxygen. All right, so again, in total, that would be 760 if we add up all the partial pressures. So Dalton's law, again, is just saying it's the sum of all the contributions of those individual gases that make up that total atmospheric pressure. Okay, so that makes up the composition of the air that we breathe, those individual gases that all contribute to the overall pressure. And so again, we call those the partial pressures. Now, when we breathe in that air from the atmosphere, those partial pressures can actually change. They undergo some changes as they enter into our airways for several reasons. First off, when we inhale, we humidify the air. All right, so as we breathe in that atmospheric air, we humidify, we're adding water vapor to it because we produce some water vapor based on our temperature and our metabolism. So we humidify that air. So when we add this water vapor to the air we breathe in, that water vapor essentially displaces some of the oxygen and the nitrogen and so on, changing its overall partial pressure, changing its overall quantity in that air. In addition, the air is also diluted. All right, it's diluted by what we call the functional residual capacity. So if you recall from the previous lecture, when we're breathing at rest, we call it tidal volume. So that's 500 mils of air in, 500 milliliters of air out, right? And I told you that we have in our lungs still what we call the functional residual capacity, which is approximately 2 to 2.5 liters of air that's still in the lung that's not moving out when we breathe out normally, okay? So when we breathe in that 500 mils, it's going to be humidified and then mix with this 2.5 liters that's still in there. So it's going to mix with that. And the functional residual capacity, because it's been in our lungs and it has undergone some gas exchange, it's lost some oxygen because that's diffused into the blood, and it's gained CO2 because CO2 is diffused out of the blood and into the alveoli. There's a higher concentration of CO2 and a lower concentration of oxygen overall. So this new fresh air is going to be mixing and being diluted by this air that's been in the lungs, okay? And we're also humidifying it. So let's take a look at this chart over here. This is showing you inspired air from the atmosphere, and it has the same percentage breakdown that we talked about, right? About 79% nitrogen, 21% oxygen, and so on, for a total of 760 millimeters of mercury. That 760 millimeters of mercury is not going to change, okay? So the pressure stays the same all the way down to the alveoli, but the mixture and the content of that air will change because of the addition of water and CO2 and the loss of oxygen and so on. So let's take a look first at oxygen. You see it's at about 21% in atmospheric, but in the alveolar air over here to the right, the percentage of oxygen has dropped. So in other words, the partial pressure of oxygen is going down. It went from 21% down to about 13 to 14%. And the reason is, as we humidify the air and add water, that displaces some of the oxygen, and the oxygen is actually being actively taken up by the capillaries there. So we're losing it, right? It's not stagnant. So you'll notice that the partial pressure of oxygen has dropped from about 159 in the atmosphere to about 104 by the time we get to the alveoli, okay? In addition, you see here's the water, about 47 millimeters of mercury. Now that's going to be sort of a standard number that you're going to see at standard body temperature metabolism. So here in the atmosphere, about 3.7 was contributing partial pressure of water, but in the body it's about 47. Okay. Here CO2 is 40. That's much, much higher than what was in the atmosphere at 0.3. Again, we're producing CO2, and that's in our alveoli. So what ends up happening is that addition of water, that addition of CO2, and no change in the total pressure here, okay? The addition of CO2 and water at those levels, and the fact that we take up the oxygen out of the alveoli, causes really the most substantial decrease in the contribution to oxygen here. So the partial pressure of oxygen goes down. All right, ultimately, we're diluting it if you want to look at it that way. Okay, so let's talk about the alveolar gas exchange now. So what this is now as we breathe that air in and it gets into the alveoli is going to then, or the gases in the alveoli are going to interface with the fluid medium of the body. Meaning, again, that starts really with the lining around the alveoli, which has some fluid. If you guys remember the surfactant and everything else, there's a little bit of fluid there. So we have an air to water interface when they get to the alveoli. And according to Henry's law, when we get to air-water interface, the amount of the gas, like CO2 or oxygen, right, that's dissolved in a liquid, or that will dissolve into our capillaries, is proportional to the partial pressure gradient. Right? So there has to be a gradient for it to want to move into the capillaries, right? So in other words, you're going to want a higher partial pressure in the alveoli than what's in the capillary, and it's going to move down its pressure gradient into the blood. We call it a partial pressure gradient to indicate that this is per individual gas. Okay, so CO2 wants to go down its pressure gradient, O2, and so on. But another factor that affects the ability of gases to move into that fluid medium is not only that there has to be a gradient, but also how soluble is that gas. So for example, if let's say I had the same exact pressure gradient for oxygen and CO2, okay, they would not necessarily have the same amount that dissolves into the fluid because they have different solubilities. So even with the same gradient, for example, CO2 is much more soluble than oxygen. So therefore, for the same gradient, you will get more CO2 dissolving into blood, all right, than you would oxygen dissolving into blood, simply because that the CO2 is far more soluble. Okay, and again, I say that that's at a given temperature. We're assuming body temperature, 37 degrees Celsius or 98.6 Fahrenheit. So we kind of just hold that as a constant. All right. So based on the pressure gradient and solubility. Okay. Now, if we take a look at this picture here, part A, this is showing you oxygen. So we have oxygen molecules above a beaker. This is to kind of represent what's happening in the alveoli. So the air above in the beaker there is representing the alveoli, and that the fluid there is representing the blood. And you see there's a high concentration of oxygen relative to what's dissolved in the blood. And so the two factors that are going to affect that is the pressure gradient and how soluble it is. And so assuming that the pressure gradient is pretty steep here, you'll notice that we're primarily going to be dissolving oxygen into that fluid. And it'll continue to do so. It'll continue to dissolve and go down its pressure gradient until we reach an equilibrium. All right, so there's no gradient there anymore. And the total amount of oxygen that ends up actually dissolving into the blood is also dependent on its solubility overall. Okay. So again, it reaches an equilibrium where no more oxygen is going to move. Now in CO2, we have the reverse because usually we're blowing CO2 off, right? We're producing CO2 in the body, so we're going from the blood into the alveoli. So that's why we're seeing, to start, more CO2 in the blood, and there's a higher partial pressure of CO2 in the blood relative to what's in the alveoli, and so the tendency is for the CO2 to leave the blood and go into the air. Okay. Now, of course, that can also reach an equilibrium as well, and once it reaches equilibrium and the partial pressures are equivalent to one another, then the flow of CO2 would stop. Now, there's actually a lot of classic examples for this. So, for example, if you like carbonated beverages, right? So CO2 is dissolved inside the drink, and they cap it off, and so the cap keeps and maintains that pressure. So there's still CO2 dissolved inside the drink, and when you take the cap off, you hear fizzing and bubbling and so on. What ends up happening is the atmosphere doesn't have as much CO2 as what's dissolved inside that beverage, and so when you remove the cap and the pressure is released, and now there's a gradient. There's a higher concentration of CO2 inside the beverage relative to the atmosphere, and so it leaves. Okay. Same thing if you chlorinate a pool. If you add a lot of chlorine, right, you're chemically adding that to the pool water, you can smell the chlorine in the air. And again, because some of that chlorine is going to equilibrate with the atmosphere, there's a gradient there. All right, now the last point I want to make is in terms of concentration of a gas that's dissolved in the liquid. Again, that's going to depend on how soluble that particular gas is. And we usually express this as the partial pressure. So the partial pressure is the pressure that's being exerted by that individual gas, but it can also represent a concentration. Okay, so for example, if let's say we have O2, so we have oxygen, and the partial pressure, we'll say, is 50 millimeters of mercury. All right, at 50 millimeters of mercury, the amount of oxygen that's actually dissolved in the blood, okay, it'll be a certain concentration, whatever that concentration happens to be. All right, but let's say I've increased the partial pressure of oxygen to 100 millimeters of mercury. Well, what's happened now is by increasing the partial pressure of oxygen, the amount that is going to dissolve in the blood is going to be greater, and so the concentration has gone up. It's actually doubled. It's in proportion. So if I double the partial pressure, I'm going to double the effective concentration that's going to be dissolved. The same goes for if I cut it in half, it's going to be halved as well. Now, what if I say we have CO2 at 50 millimeters of mercury? All right, so let's say we have oxygen and CO2 both at 50 millimeters of mercury. That's our partial pressure, excuse me. Does the 50 millimeters of mercury of oxygen that's dissolved represent the same concentration of CO2 that will be dissolved at 50 millimeters of mercury? No, it doesn't, because they have different solubilities. So in fact, since CO2 is more soluble, at 50 millimeters of mercury, I would have a higher content of CO2 in the blood compared to, say, oxygen. So they don't represent a specific concentration of all gases. So I can't say 50 millimeters of mercury is the same concentration across all gases, CO2, nitrogen, or oxygen, because it depends on their solubility. So at 50 millimeters of mercury, oxygen, it'll represent a specific concentration, but that concentration is going to be different from 50 millimeters of mercury of CO2. But what I can say is within the same gas, right, if I take CO2 and I increase it to 100 millimeters of mercury, what I can say is that the CO2, if it goes from 50 to 100, that there is an increase in the concentration of CO2 and it's been doubled. Okay, but I can't cross-compare concentrations using partial pressures. I can't compare 50 millimeters of mercury O2 compared to 50 millimeters of mercury CO2, because those concentrations are not the same. All right, again, it depends on that solubility. Okay, so what I want to show you with this is now how the partial pressures of oxygen change as we inspire that air, what it looks like in the lung, what it looks like in the arteries and in the veins. So first, if we take the inspired air, okay, you see that the inspired air, the partial pressure of oxygen is 159, and that's at sea level, so 21% of 760. When we breathe that in, I already told you it gets humidified and it gets diluted by the functional residual capacity. And so the partial pressure of oxygen is 104. And now I'm only looking at oxygen right now. We'll talk about CO2 next. So if we're in the alveoli, let me draw that over here. So I have the alveoli. I'm going to draw it like this. Let's pretend that's the alveoli, and this is the capillary. So the partial pressure of oxygen in the alveoli by the time it gets there is about 104. Okay. And so we have the capillary here, so let's say blood is moving in this direction. Now, the venous blood, or the deoxygenated blood, I'll say, that has a partial pressure of oxygen of 40 millimeters of mercury at rest. Okay, these are resting conditions. We're not talking about exercising. So about 40 millimeters of mercury of oxygen. And you can see from this, there is a partial pressure gradient, right? So we talked about that in Henry's law, how if I want that to go from gas and dissolve into the fluid, there needs to be that gradient, and you can see that gradient right here. So there's a higher gradient inside the alveoli relative to what's in the capillary, and so oxygen is going to diffuse directly into the solution. So it's dissolving into the plasma of the blood. Okay, so as it does so, by the time we reach the end of the capillary, it will have equilibrated. All right, it'll have gone down its concentration gradient, and by the end of the capillary, now we're getting the oxygenated blood. The partial pressure of oxygen at the end of that capillary as it's leaving the alveoli is going to be 104. Now you may be saying to yourself, okay, well, you know, if oxygen is moving out of the alveoli and into the capillary, and then the alveoli pressure must be going down as the capillary pressure goes up, and they probably should meet somewhere in between. But the reality is that that doesn't happen. It actually goes all the way to 104. And the reason for that is that we're still breathing. So it's a dynamic process. As we're inspiring, we're breathing in new, fresh oxygen. That's the actual act of ventilating and breathing and continually breathing is replenishing the oxygen in the alveoli. So this remains more constant based on our respiratory pattern. So that 104 millimeters of mercury in the alveoli is maintained by our ventilation. Okay? So you can imagine if I change the way I ventilate, I could change the partial pressure of oxygen in the alveoli there. But because I'm continually replenishing that oxygen in the alveoli, it doesn't decrease in amount at standard resting conditions. So therefore, we're going to continually add more and more oxygen to the blood as it's going through the capillary, and it'll equilibrate with what's in the alveoli at 104. So back and look at the cartoon here, you'll see that the oxygenated blood over here, now they're saying it's about 95 millimeters of mercury, not exactly 104. Now the reason it's 95 is going to be slightly less, and I'm going to get into more detail on that in a little bit later, but just suffice to say now that some of the oxygenated blood does mix with a little bit of venous blood, and so the average kind of comes down a little bit. So instead of being exactly 104, it's a little bit less, and that's typically about 95 millimeters of mercury. Okay. Now, as it gets into the left side of the heart and gets pumped out systemically, that partial pressure of oxygen is still 95 as it's heading towards the tissue, towards the capillaries. So I'm going to draw another diagram down here. So this is the capillary, so we're talking about the tissue down here. I'm going to just draw some squares to represent, these just represent cells, okay? And we'll say that the blood is moving in this direction, and it's coming in at 95 millimeters of mercury. So it's 95. And again, it's a little bit lower because when all those capillaries coalesce and come together, some of it mixes with venous blood, so that's why it's dropped to 95. Now, once we get 95 millimeters of mercury oxygen on the arterial side of the capillary, in the interstitial, we actually have a partial pressure of 40 millimeters of mercury of oxygen in the interstitium, and in the cell itself about 1. So here's our gradient. The interstitial oxygen is going to move into the cells down its partial pressure gradient, and the oxygen is going to move from the capillary into the interstitial down its partial pressure gradient. So it's moving like this. It's going down its gradient, and then this would, of course, go down its gradient. So the cells are continually using up the oxygen, and so therefore that would drop the oxygen content in the interstitium, but that's constantly being replenished by the capillary oxygen moving into the interstitium. So we maintain that gradient. Okay, so as it moves down, by the time we reach the end of the capillary, so on the venule side, it's going to be the same as what's in the interstitium, so it's going to be about 40 millimeters of mercury. So that is going to be the oxygen partial pressure at the end of the capillary on the venule side, and that's what's going to return to the lungs. So that's what you're seeing up here is that 40 millimeters of mercury. Okay, and then again, that's going to be replenished by the partial pressure of oxygen being in the alveoli being higher than that, and so the oxygen will diffuse into the blood there. And so this is basically the cycle that returns. And if we take a look here in the cartoon, you'll see that the partial pressure of oxygen in the venous blood is about 40 millimeters of mercury right there. Okay. Now, for CO2, so let's talk about the CO2 quickly. I'm going to get rid of some of the numbers for oxygen so we don't get confused here. Okay. Now let's talk about CO2. So CO2, remember, there's very little in the atmosphere itself. We're pretty much just producing that. So I'm going to start in the tissue side of it, since that's where the CO2 is really being produced. So remember, these cells over here, I'm just going to put X over here, these cells here are producing CO2, and the CO2 is accumulating in the interstitial space there. It diffuses out of the cell and can accumulate. And the CO2 can accumulate to typically about 46 millimeters of mercury. Okay? So what happens is, if it's accumulated about 46 millimeters of mercury, that readily diffuses into the capillary. So we say this is the capillary at the venule side here. It's going to be about 46 millimeters of mercury, again, because we're in an equilibrium state between what's being produced by the cell, moved into the interstitium, and then moved out of the interstitium and into the capillary. And under resting conditions, that's 46 millimeters of mercury. That 46 millimeters of mercury is going to be in the venous blood, returning to the lungs. And in the alveoli, if you look back a few slides, all right, the alveoli partial pressure of CO2 is 40 millimeters of mercury. Now, here's our gradient. We have 46 to 40, so CO2 is going to move down its partial pressure gradient and into the alveoli. So what's happening here is, again, it's dynamic. Our bodies are producing CO2 at the cellular level. That gets distributed into the capillaries, brought to the lungs at a high partial pressure. That then moves into the alveoli, and it's again our ventilation that maintains that partial pressure of CO2 in the alveoli. So at standard resting ventilation, that partial pressure of CO2 is going to be 40. If we were to increase ventilation, breathe faster, we would blow off more CO2, and so the partial pressure of CO2 in the alveoli would go down. If we were to breathe less, we'd retain more CO2 there and change the gradient. But under standard conditions, resting conditions, our gradient is 46 in the deoxygenated blood, and 40 in the alveoli. So it moves out of the capillary there and into the alveoli, so we can breathe it off. At the end of that, at the end of the capillary there, it would be equal to what's in the alveoli at 40. All right, so that's 40 millimeters of mercury of CO2. So we don't get rid of all of it. All right, we get rid of a portion of it. So that's 40 millimeters of mercury now that's going to be in the arterial system. And if we look at the cartoon over here, right, here's our oxygenated blood. Right, there's a partial pressure of CO2 of about 40, and that's our typical amount. And then that same 40 here when it reaches the tissue, right? So it'll be 40 on the arterial side of the capillary, and since the interstitial tissue is 46, again, that's why CO2 is moving down its partial pressure gradient into the capillary fluid, which is 40, and so it equilibrates at 46, comes back to the lungs, gets rid of some of that CO2, back to 40, and so on. So this is the cycle that repeats itself. And just quickly, if you look over at the cartoon here, the deoxygenated blood, the partial pressure of CO2 is 46. Okay, so these are the partial pressures of oxygen and CO2 as it circulates in our blood under standard conditions of resting conditions at sea level. Okay, so we talked a little bit about now how the partial pressure gradient affects the diffusion of gases moving down its gradient into the blood, or from the blood into the alveoli. So general properties of diffusion, all right, things that will affect gases' ability to diffuse. All right, first off, if there is an increased in gradient, so that's what we spoke about, right? So if I increase the partial pressure gradient, I increase the driving force of the gas to move down that gradient. The solubility, right? How soluble is it? So those are two factors we've already spoken about. So if I increase the solubility of a gas, then more of it can actually dissolve into the solution or diffuse. The increased surface area. All right, so increased surface area, again, this is the lungs are not two open containers, right? That would actually be very little surface area relative to what we actually have, which is all these millions and millions of alveoli, and these tiny little alveoli increase the surface area greatly. And so this allows for greater gas exchange. And you can imagine anybody with a particular disease where it's destroying the alveoli, the alveolar walls, they're losing surface area. So they're actually decreasing their ability to diffuse gas or intake oxygen or get rid of CO2. In fact, this cartoon over here is showing you that. So here's emphysema, which is some type of COPD or chronic obstructive pulmonary disease. And this is looking at a histological section of the alveoli. And up here is actually what the normal should look like. And you can see all these alveoli in cross section, all right? And these walls, the walls of the alveoli are very thin, which are surrounded by a whole bunch of capillaries, so we can increase our diffusion. And you'll notice that these walls they're missing. There's a lot of pieces missing there. That's going to decrease our surface area and inhibit our ability to diffuse as readily. Now, finally, the last piece is if there's an increase in membrane thickness. So the thicker the membrane is, or the thicker the wall of the capillary, for example, the longer it takes for diffusion to happen. It makes it less efficient. So in this middle cartoon right here, what you're seeing is like pneumonia, where you could have inflammation and thickening of the wall there, as well as excess fluid buildup in the alveoli itself, and that actually contributes to increasing the distance of diffusion, which means it's going to take longer, right? And so that can actually work against us and decrease the amount of diffusion that takes place. All right. So basically, diffusion is directly proportional to the gradient, its solubility, and the surface area. It's inversely proportional to the membrane thickness. And the last thing over here is this ventilation-perfusion coupling, which I'm going to get more into in the next lecture. But the V stands for ventilation, and the Q stands for perfusion. And what this is really just indicating is that we want to match as closely as possible the airflow, the ventilation that's going into the alveoli, relative to the blood flow, right? So we want good blood flow past the capillary while it's getting good airflow, and as long as that's fairly matched, right, then we'll have good exchange as well. As we call this VQ, or ventilation perfusion coupling. So quick example, if for instance I have something obstructing one of the alveoli, so there's no ventilation into the alveoli, there's no air getting into the alveoli, but I still have blood flow going past that alveoli, there's not going to be any gas exchange, it's not going to pick up any oxygen. So if it's not picking up any oxygen, this is referred to as a shunt. I mean, essentially what you're having is blood that's going past an alveoli that's not providing any oxygen, so the blood that leaves that alveoli is not becoming oxygenated. And so in that case, what this ratio reflects on that is that since ventilation has gone to 0 in that alveoli, right, 0 divided by anything is 0, so our ventilation perfusion would be 0. And so we'll go through more examples of that and how, if we change perfusion, what happens to the ventilation and so on. But that ratio is actually very important for us clinically and diagnostically. And then the box down here, this is showing you a low PaO2. 2 parts of the lung result in vasoconstriction to shunt blood to oxygenated areas. This is really a critical concept. So first off, I want to just point out that when I say PaO2, and you see a capital A, it's the partial pressure of oxygen, but the capital A here indicates that this is the partial pressure of oxygen in the alveoli. So that's usually how we write that. If on the other hand it was partial pressure of oxygen and there's a lowercase a, that's to indicate the partial pressure of oxygen in the artery. So it's good to remember the capital A versus the lowercase a there. Now, we've talked about this in the cardiovascular lectures. In the body, at the tissue levels, not including the lung, but all the other tissues of the body, if they're low level of oxygen and high levels of CO2 and so on, that's going to increase blood flow to those organs so that they can exchange and get that oxygen and get rid of the CO2. So they increase, so they dilate vessels going to those organs in order to increase their flow when they're low on oxygen. But the lungs don't behave in that way. So the lungs actually do the reverse. And it makes sense, all right? So for example, if a portion of the lung is not oxygenating well, so some of the alveoli are, let's say, blocked or occluded or what have you, but they're not getting good oxygen, what happens is those low oxygen areas of the lung, they vasoconstrict. They vasoconstrict, and what that does, that blocks flow to the areas of the lungs that aren't getting ventilated well, and shunts the blood to areas that are being ventilated well. Because the whole purpose of the lung is to exchange those gases. So if a part of the lung is not exchanging the gas, it shuts off blood flow or reduces that blood flow to that area and shunts it to the areas that are getting gas exchange. So that way we can still get oxygen and get rid of the CO2. So in terms of the lung, it's a little bit of a reverse of what we talked about with the rest of the body. We're going to actually constrict our blood flow to areas that are not being well oxygenated, and we'll shunt the blood to the areas that are, so we can make sure that we get that oxygen. So this graph is actually showing you how the partial pressure gradients can change based on the atmospheric pressure. So here on the y-axis, you see we have partial pressure of oxygen in millimeters of mercury. So let's take a look at the middle line first, at the blue line. The partial pressure of oxygen at 158. And so this is the atmospheric pressure at sea level. Remember, that's 21% of 760. It's about 158 or 159. So that's air at sea level. Again, we can call that 1 atmosphere. So that's sort of the top that we could reach at sea level. And it's showing you over here, this is the pressure gradient of oxygen from the atmosphere into venous blood. And if you recall, in the venous blood, at resting conditions, the partial pressure of oxygen is going to be 40. That's the deoxygenated blood returning to the lungs. So that's why you see it's at the level of 40 here. So it's basically telling you, well, this is the gradient that would be set up in the atmosphere relative to the partial pressure of oxygen in the deoxygenated blood returning to the lungs. And so it creates a slope, so you can see that slope right there. Okay, and so that's effectively our atmospheric gradient from the atmosphere into our blood. Now, if you take a look here at 110, this is at 10,000 feet, so we're at a higher elevation. And so at higher elevation, the partial pressure of oxygen is going to be reduced because the total atmospheric pressure is reduced. So instead of being 760 millimeters of mercury, at 10,000 feet, it's like 523 millimeters of mercury. And so 21% of 523 is somewhere around here, or about 110 or so. And so that's going to be the top part of the gradient. And again, the venous doesn't change. All right, that returning blood doesn't change. It's still 40. So you'll notice that the slope is decreased because our gradient has come down slightly. And this is actually what happens as we go to higher and higher altitudes. The gradient continues to drop because the amount of oxygen that's actually present in the atmosphere goes down. And our gradient can actually completely flatline if we go to a high enough altitudes where there is no gradient anymore. We can't get good exchange. Now, we could go in the reverse direction. So in the reverse direction, what we would use this clinically is something called like a hyperbaric chamber, for example, where we can actually artificially increase the pressure. All right, we can increase the pressure in the person. And you can see in this example, they've increased the pressure to 3 atmospheres. So in millimeters of mercury, that's 760 times 3. And they're also changing it to 100% oxygen. Instead of 21%, they're making it all oxygen. So 100%, so 760 times 3, and that's all oxygen. So that increases the gradient greatly here. All right, you can see it's just under 2,500 millimeters of mercury there. And you see how steep that gradient is. And this would really drive oxygen in. So even though oxygen is not as soluble, say something like CO2, we can drive in more and more oxygen if we can really increase that gradient. And so in certain clinical situations, something like this might be used where we really want to drive in that oxygen. So now in terms of gas transport, what we're talking about with this is that there's a process of carrying O2 and CO2 from the lungs to the tissue or from the tissue back to the lungs. And there's a specific process for that. What we've really been talking about up until this point is that CO2 and O2 dissolve directly into the plasma. And so that's only going to make up a small percent of the total quantity of oxygen or total quantity of CO2 that's in your blood. The rest of it, the other quantity of CO2 or of O2 is made up of the fact that O2, for example, binds to something else. And this greatly increases the capacity to carry oxygen in the blood or to increase the quantity of oxygen that could be in the blood. Okay, so here, oxygen is transported almost 100%, but it's not. It's about 98.5% bound to hemoglobin. All right, and on average we have about 15 grams per deciliter of hemoglobin. Right, that's found inside our red blood cells, and so we know that this has high affinity for oxygen, and so oxygen molecules will actually bind directly to this hemoglobin, and this greatly increases our capacity to keep oxygen in the blood. Okay. And so we call this our content of oxygen. It's part of what makes up the content of the oxygen in the blood, or the quantity of oxygen in the blood. And the majority of that comes from the fact that hemoglobin can bind to the oxygen and hold on to it. Okay. The other 1.5% is directly dissolved. So that's what we've been talking about so far, was oxygen coming into the arteries, for example, and dissolving directly into the plasma. That actually only makes up about 1.5% of the total quantity of oxygen. The other 98.5% comes from the fact that it binds to hemoglobin. But there's another key point here is this. All right. When we talk about partial pressures, the partial pressures of oxygen or the partial pressure of CO2 is only contributed by the dissolved unbound oxygen, or CO2. All right, it's just what's directly dissolved in the plasma. So for example, the partial pressure of oxygen in the arteries is 95 millimeters of mercury, right? So that's what we went over. That 95 millimeters of mercury is pressure that's exerted by the dissolved oxygen in the plasma directly. This 1.5%, all right, is creating that much pressure. Once oxygen is bound to something like hemoglobin, it no longer exerts a partial pressure anymore. Hemoglobin in this case, though, is going to greatly enhance our capacity to carry blood. It no longer contributes to the partial pressure, but it does contribute to the total oxygen carrying capacity we're going to have. So it greatly increases the quantity that's in our blood. So to put a number to that, it's about 20.1 milliliters of oxygen for every deciliter, or every 100 mLs. The dissolved oxygen is about 1.5%, right? So that's, in terms of quantity, that's about 0.3 milliliters of oxygen for every deciliter. So it's far less in terms of total oxygen amount is directly dissolved. The rest of it is primarily bound to hemoglobin. And hemoglobin, just in brief, right, specialized for oxygen transport. There's these 4 globin portions, right, primarily those alpha and beta globins. They have a heme group, and so that heme group has an iron at its center, and each one of those heme groups has 4 hemes, can bind to 1 oxygen molecule. So that means 1 hemoglobin molecule made up of those 4 hemes with 4 iron centers can bind up to a maximum of 4 oxygen molecules. All right, so every hemoglobin molecule, 4 oxygen molecules. We can also talk about hemoglobin in terms of its saturation, right? So on the previous slide, I talked about it in terms of quantity of oxygen, right? 98.5% of the oxygen found in the blood is carried by the hemoglobin. And in the arterial side, that comes out to about 20.1 milliliters per deciliter. Now, in terms of saturation, what this is saying is like, all right, well, if I have all of my hemoglobin is completely saturated with oxygen, so it's bound to 4 oxygen molecules each, then it's going to be 100% saturated, right? Every single hemoglobin molecule is fully saturated with 4 oxygen molecules. If, on the other hand, there's only 3 bound to a hemoglobin molecule, it's 75% saturated. So the math there is fairly simple. It's fairly straightforward. If only 2 are bound, it's 50%, and then 25%, and so on. And so we can actually measure saturation clinically. Right? We put the little sensor on, and it can tell you that their saturation is, say, 85%. What that really means is it's an average of the total, because some hemoglobin molecules are going to be 100% saturated, some are going to be 50%, some are going to be 75%. You take the average of all that, it's going to come out to somewhere, let's say, an 80 or 90% saturation or something. Okay, but this tells us how much oxygen is actually bound to the hemoglobin molecule. So that's how this differs slightly from the amount of hemoglobin. So saturation versus total amount, right? Total amount of oxygen that's actually there, right? If we have normal amounts of hemoglobin and they're bound to oxygen, it's going to give us a certain amount or a certain quantity of oxygen. So the example I gave was about 20.1 mils of oxygen per every deciliter. Here, in saturation, it's how much oxygen is actually bound to the hemoglobins at any given time. So just a quick example of how we compare these two and where they can differ is, for example, you can have somebody who is anemic, meaning their red blood cell content is low, meaning they don't have as much red blood cells, they don't have as much hemoglobin, so they can't bind as much oxygen. So the quantity of oxygen would be lower, simply because they have less hemoglobin to bind to the oxygen. However, the hemoglobin that's there, that's actually present, although it's in lower concentrations, could be fully saturated. So you could have somebody who's anemic, and hypoxic, meaning they're not getting enough oxygen because they don't have enough hemoglobin to carry enough oxygen for the body. However, the hemoglobin that's there is fully saturated. It could be 100% saturated. All right, so this is how it could differ from one another. So we can kind of compare and contrast that, saturation levels versus total amounts and so on. So I'll give some more examples of that during more of our live interaction. What you're seeing on this graph is called a oxyhemoglobin dissociation curve. And so I'm going to start with the one on the left. This is a graphical representation of how the partial pressures of oxygen can affect how oxygen directly dissolves in the blood and how oxygen binds to hemoglobin. So first, if you take a look at the left graph here, you can see on the x-axis is the partial pressure of oxygen. And then over here on the y-axis, on this graph, you have volume percent. Volume percent simply means mils per deciliter, so it's looking at a quantity of oxygen. And you see it goes anywhere from 0 up to about 20.4 in this example. So just quickly, how we get to that number is this. I told you on the earlier slides that we have about 15 grams per deciliter of 15 grams of hemoglobin, per deciliter. Now there's actually about 1.34, and this is numbers I'm giving you, 1.34 mils of O2 per gram of hemoglobin. So obviously the grams of hemoglobin are going to cross out here. And what we're left with is 20.1 mils of O2 per deciliter. And this said 20.4, so we're pretty close. What we have to calculate for now is the final piece. If you recall, that would be the final amount of oxygen directly dissolved, which I told you on the previous slide was 0.3 mils of O2 per deciliter. So 20.1 plus 0.3 of dissolved comes out to 20.4 as our total. So that's telling us the total quantity of oxygen that's dissolved. That's dissolved and bound to hemoglobin. So you can see the dissolved portion is actually a linear curve, so I don't want you guys to miss it. It's right down there. It says O2 physically dissolved in solution. So what you're seeing is as the partial pressure of oxygen increases, all right, as it increases, the concentration goes up, or the amount dissolved in solution increases linearly in proportion to that, which is something what we talked about with Henry's law and so on. So you can see, but that amount is still very, very small because it's not very, very soluble. So the way to increase the amount of oxygen we can actually have in the blood and increase that content of oxygen, right, or increase that quantity, we have to look at this curve over here. And it is sigmoid in shape, and that's due to the relationship that oxygen binding to hemoglobin has. So for example, remember each hemoglobin molecule has 4 binding sites. And so there's something called positive cooperativity, wherein as one oxygen molecule binds to the heme group, it increases the affinity of oxygen for the other hemes. So, and that goes for every step of the way. So as another oxygen molecule binds, that increases the affinity still further and further. And so what you see is this fast increasing upward slope as we're increasing the affinity at these partial pressures. Now, you notice, of course, it's going to plateau because ultimately there's just a finite amount of hemoglobin in the body. Now, as we look over here, all right, on the x-axis, we have a partial pressure of oxygen of 100, which is approximately the partial pressure in the alveoli and what the capillary partial pressure is going to be when it's leaving the lungs, so in the arterial system as well. So it's approximately 100. We're just averaging here. All right, so it's about 100. So that's why you see this little circle here on the hemoglobin curve at A. It's showing you that, yes, on this linear line down here, that concentration is going to be somewhere about 0.3 mils of oxygen that's directly dissolved based on that partial pressure gradient. On the other hand, over here, the amount of oxygen that's bound to hemoglobin is about 20.1, okay, based on our calculation over here. So it can hold on to a much higher concentration. And then you'll notice that the partial pressure drops, and it drops to about 40, which you're seeing right here. That coincides We'll move some of these arrows out of the way first. That coincides with the venous partial pressure of oxygen. If you recall, that's about 40 millimeters of mercury. All right, so when we see the partial pressure of oxygen drop, and we can take a look. This actually shows us if the partial pressure of oxygen in the venous blood, quote unquote, our deoxygenated blood, what is the quantity of oxygen that's in those veins? Well, if you take a look at that, all right, that's going to be approximately about 15 mils per deciliter there. So in other words, when we call venous blood under resting standard conditions deoxygenated, it's a little bit of a misnomer. It's not actually deoxygenated. It still has about 75% of that quantity there, right? So 15 out of 20. So really, under normal resting metabolism, we only take off or use up about 5 mils per deciliter during normal resting metabolism. And again, that's moving from the arterial partial pressure of 100 all the way to the venous partial pressure of 40. So even though we have a drop in partial pressure that looks very large, like 100 all the way to 40, the actual amount that we've lost in terms of quantity at rest is really only about 5 mils per deciliter. Now, if we look over here to the right, you'll notice the curve looks exactly the same. We have partial pressure on the x-axis. Again, that's the arterial. Here's the venous side of the partial pressures. Okay, and the curve looks identical. The only difference is, when we look at the y-axis, we're looking at percent saturation. So again, this is that quantity versus saturation that I talked about earlier. So this is the actual amount of oxygen bound to the heme there. And so this directly correlates, and it would make sense. So if you look at this, as we go from 100%, partial pressure of 100 millimeters of mercury in the arterial system, and we drop to about 40, what is our saturation in the venous? So if there's 40 millimeters of mercury of oxygen in the venous system, well, that coincides with about 75% saturation. So in other words, in our venous blood, our low oxygen blood, we really still have, in terms of quantity, about 15 mils per deciliter. In terms of saturation, it's still 75% saturated. Now, this is actually important, a point to make, because this is what it looks like at rest. This also gives us a reservoir for if we were to increase demand suddenly. So, for example, under resting conditions, we're still 75% saturated. If the demand suddenly goes up, okay, and if we have any kind of impairments in gas exchange there, we're still able to circulate and deliver more oxygen. All right, we can still deliver 75% of what's left. All right, so it does give us some leeway. Now, this is how tissues normally behave at rest, but these conditions would change, obviously, if we're exerting ourselves and the demands for oxygen go up. So oftentimes you'll see both curves drawn together. So on one y-axis you'll see volume percent, which is just the quantity, and then on the other side you'd see percent saturation, since the curves look essentially identical there. And you can see how saturation and quantity are affected by the changes in partial pressure, how they relate. The last thing I want to point out before I move on from this, though, is coming back to the sigmoid shape of the curve. You'll notice that at the higher partial pressures, we're effectively from, let's say, about 60 millimeters of mercury. I'm doing it on the right side, so you can see, from about 60 or so to up to about 100 here. You'll notice that we're at what we call a plateau, or fairly flat phase right there. And this is actually an ideal situation for us, because even drastic changes in our partial pressure, which can occur in the atmosphere, if say we're traveling, we're going to higher altitudes or something like that, drastic changes in the partial pressure of oxygen in our atmosphere do not drastically change the saturation or the quantity of oxygen that's dissolving in the blood. And you can see that, because if we go all the way to 60 millimeters of mercury, if you were to draw a line here at 60, right, we can still be close to 90% saturated, which again can be somewhere around 18 or 19 mils per deciliter. So the quantity doesn't change all that much, even for large changes in our partial pressure of our atmosphere. So it helps act as a buffer for our atmospheric changes. And the flip side to that is this: at the tissue level, at 40 millimeters of mercury, which you're seeing right down here, right, that's our common partial pressure in our venous system. we're usually about 75% saturated. What if the tissue demand for oxygen has gone up? So instead of being at 40, the partial pressure of oxygen is going to decrease even further because we're utilizing more and more oxygen, so we're decreasing that even further. So let's say we decrease it all the way to 30 right here. Just a decrease of 10 at the tissue level. Well, that decrease in 10, if I draw a line straight up from there, it's going to be somewhere around here, close to 50% saturation. In other words, from the arterial side to the venous side, I had a change from 100 all the way to 40 millimeters of mercury. And the total saturation was about 75%. So 25% was actually given off to the tissues. But let's say the tissues were to work even harder so that they extract even more. Even if I went another 10 millimeters of mercury further, so say from 40 to 30, that difference of 10 millimeters of mercury, I dropped almost another 25% in saturation because of the point I am on this curve. Right? It's a steeper portion of the curve. This is also ideal at the tissues because if the tissue demand goes up, I can extract more readily. It unloads more readily. So for a given partial pressure difference, I'm going to unload more oxygen because I'm on the steeper part of the curve. So this is sort of an ideal situation where at the plateau, I can withstand changes in partial pressure and still essentially saturate or load up my oxygen into the blood. And at the tissue level, I can actually give off more oxygen for very little change in partial pressure. And it's all because of the shape of this curve and the relationship hemoglobin has with oxygen. So this is showing you the same curve, okay, but instead of showing you two separate curves for the quantity and the saturation, it's just combined them. So when you're reading it, you just have to look at the different axes. So over here, on the left-hand side, you see it's percent saturation of the hemoglobin, and on this side, it's the oxygen content, or the quantity of oxygen. Again, in mils per deciliter is our quantity units. And so here, partial pressure of oxygen at 100, you can see that that's really where the blood in the alveoli would be about matched. So the arterial blood, the oxygenated blood in our systemic circulation, all right, close to about 100 millimeters of mercury. And then here, tissues at rest. Again, resting conditions, resting metabolism, it would drop the partial pressures of oxygen to about 40. And you can see whereabouts on the line that falls right there, which coincides with 75% saturation, which is a loss in quantity of about 5 mils per deciliter over here. So that's all things that I've mentioned before. So again, resting physiologic range. If we have atmospheric changes, we go to higher altitudes, the partial pressure with which we're breathing could change. So instead of being at 100 mils, we could be at 80. But even if we're at 80, again, because the partial pressure gradient has gone down at higher atmosphere, you'll notice that our saturation is still pretty close to the same. Okay, the quantity is still pretty close to the same. So that's that buffer region I was talking about. And at rest, we could still be using up 40. Okay, but if we increase the amount of activity we're doing, we could extract more. So instead of going from, say, 100 millimeters of mercury partial pressure of oxygen dropping to 40, we might go from 100 to 30. Now if we go to 30, because the tissue is extracting more, that simple change of 10 millimeters of mercury has significantly given up more oxygen, right? So instead of being 75% saturated, we're at 50% saturation, and our concentration is at 10. So we're on the steeper part of the curve, so the response is greater there. And again, this is ideal for working tissue because we can extract oxygen more readily. Okay, so let's now look visually at what's happening, how oxygen is moving down its partial pressure gradient, and then how that partial pressure is affecting the loading of oxygen onto hemoglobin. And this is from your notes. So if you look over here at step 1, we're breathing in, all right, so we're ventilating, so we have an increase in the oxygen content there relative to our capillary, which you can see just next to it. Okay, so the concentration or the partial pressure is higher in the alveoli, so it's going to move down its partial pressure gradient, as you can see over here in step 2. So what happens now is oxygen is diffusing out of the alveoli and entering into the plasma of the blood where it's directly dissolving. And it'll continue to do so and continue to dissolve into the blood until the partial pressures are equivalent. And we talked about that. So that's what this is showing you here. Remembering that the partial pressure of oxygen in the alveoli, which is the capital A, and this is the partial pressure of the artery, which is that lowercase a, they're going to become equivalent. And all that's reflecting is what's dissolved directly into the plasma, and that's that linear portion of the curve we talked about. Whereas the partial pressures go up inside the artery, right? We're getting slightly more dissolved oxygen, all the way up to about 100 at sea level. Now, the reason we can get more oxygen actually, or we can carry more oxygen, is because of the hemoglobin that's there, right? So this is the next part, is step 3. The oxygen that's dissolving, right, as it's diffusing from the alveoli into the blood, it goes from alveoli, dissolves directly into the plasma. The next step is from the plasma, it's going to bind to the hemoglobin in the red blood cell. So the next step is, as it's dissolving, it's going to transfer to the hemoglobin. All right, it's going to transfer, into the red blood cell and bind to the hemoglobin. Okay, so this is actually an important step, is that as we increase the partial pressure of oxygen that's dissolved in the blood, that influences how the oxygen is going to move and bind to the hemoglobin. So as the partial pressures go up and we get more and more dissolved oxygen, that's increasing the gradient for oxygen to move into the red blood cell and bind to the hemoglobin. And then, of course, the hemoglobin, based on its property, is going to bind to oxygen more and more readily. The affinity increases as that goes on. So again, alveoli dissolve first, then bind to the hemoglobin. And when that happens, you get this curve over here, which we talked about, which is that sigmoid curve based on the properties of hemoglobin and oxygen binding. And then lastly, when we get to the tissue, that's step 4. What's happening here now is oxygen that's in the dissolved state is going to leave and go down its partial pressure gradient into the interstitial fluid. So that's what you're seeing here. All right, it's going down its partial pressure gradient to the interstitium, which is then, of course, going to move inside the cell, which is using up that oxygen. So that's the gradient right there. Hemoglobin, as the partial pressure of oxygen decreases because it's going down its partial pressure gradient, since that partial pressure of oxygen is dropping in the blood, that's going to cause some unloading of oxygen from hemoglobin to dissolve directly into the plasma. So there is a balance between the partial pressure of the dissolved and how much is actually going to stay bound to the hemoglobin. So as the partial pressure goes down in the plasma, the hemoglobin is going to dissociate with some of the oxygen. It's going to go down its partial pressure. It's going to go down, excuse me, it's going to leave the hemoglobin and dissolve into the oxygen to replace it. So there's a balance between those two. So the unloading would be from hemoglobin into the plasma, from the plasma into the interstitial fluid there, and then ultimately into the cell. And it's just going to follow the same curve we talked about, but going down a decreasing partial pressure gradient here. So to kind of summarize what we just talked about, is ultimately the loading of oxygen onto hemoglobin is dependent on the partial pressures or the dissolved oxygen of the blood. So as that goes up, that's going to increase the loading of oxygen onto hemoglobin. As that pressure drops, it's going to increase the unloading of oxygen. Okay, so I've kind of already alluded to this already, but when I talked about how at the tissue level, more oxygen is going to unload from hemoglobin to active tissue. In other words, the question is this: how does the red blood cell know, quote unquote, know to unload its oxygen more to some tissue than to others? And it's not really a matter of knowing, it's really just a matter of demand. And the way we know that demand is because if tissue is more metabolic, it's going to produce more things like CO2 and lactic acid. Anything that's more metabolically active generates more heat. Because of the lactic acid buildup, you're going to decrease the pH. So things like pH, lactic acid, CO2, and all this are all indicators of metabolizing tissue. It just so happens that these indicators also happen to be the intermediates that affect oxygen unloading. It'll increase the unloading of oxygen of hemoglobin. So as that blood goes through that highly metabolic tissue, it's going to unload more oxygen. It's going to release more. Okay. So that's what this is really referring to here, is these 4 factors, all right, that adjust the rate of unloading to match that tissue demand. So for example, if the tissue PO2 is low, it's going to increase the gradient for oxygen, right? So it's going to help to unload that oxygen. So again, active tissue uses up more oxygen. So more oxygen is going to be released from the hemoglobin. So logically, it makes sense. An increase in temperature when you have an increase in metabolism, right? So heat promotes oxygen unloading. You're producing lactic acid and acid byproducts, so acidity or decrease in the pH. That's going to increase, the promotion of, or excuse me, going to increase the unloading of oxygen as well. CO2 is along with that. We're going to talk about that. That's coming up next, is how CO2 and pH are related. All right, but an increase in CO2 is going to help to unload that oxygen. And then there's also this molecule called diphosphoglycerate, or 2,3-DPG, which is found in the red blood cells. And it's a molecule that can actually bind to hemoglobin and lower hemoglobin's affinity for oxygen. So it helps it to release it more readily. And so this is going to help any of these unloading. So if you're exercising, for example, your levels of 2,3-DPG could go up in your red blood cells, which helps to unload them even more quickly, in addition to all these other factors. Here's the oxyhemoglobin dissociation curve now, but now we're referring to what's happening or how this curve is being affected by an increase in metabolism. So you're going to get a right shift. All right, you can see over here a right shift. In other words, a reduced affinity for oxygen. So to reduce the affinity, it's all the things I just talked about. Increase in temperature, which you see here, an increase in the 2,3-DPG, an increase in hydrogen ion concentration, which is actually a decrease in your pH. Okay, so these are things that would lower the affinity for oxygen so they more readily release it to working tissue. So this is a great mechanism to have, and you'll see that the curve, that gray dotted line there, shifts to the right. So that for any particular partial pressure gradient, partial pressure, I've given up more oxygen. So for example, at 40 millimeters of mercury, partial pressure right about here, compared to say our normal, which is about approximately there. So instead of being 70 or 75%, it's dropped to about 60% or so. All right, so it's given up more oxygen at the same partial pressure. So it's influenced that. Now a left shift, which you can see over here, you could increase the affinity for oxygen, so it's less likely to give up its oxygen. So that would be really the reverse of everything we just talked about. So if there's a decrease in temperature, so colder temperatures, a decrease in 2,3-DPG, an increase in your pH, and then specifically carbon monoxide is sort of a classic example. So carbon monoxide binds with very high affinity to hemoglobin, reduces the ability for oxygen to actually bind, but the oxygen that's bound to hemoglobin in the presence of carbon monoxide doesn't get released readily. So it shifts everything to the left. So this just makes it less likely to release its oxygen. Now, under sort of standard conditions, we'd be on the black line there under resting conditions. But if we were to say exercise, where metabolism is increased, you can see a shift in the curve to match that demand. And at the bottom there, I put something called a Bohr effect. So what this is saying, at the tissue level, the Bohr effect takes place, where we get the release of oxygen in response to elevated CO2. In other words, as the tissue is metabolizing more, it more readily lets go of its oxygen. They refer to that as the Bohr effect. Now, in terms of CO2, so we talk about oxygen, primarily bound to hemoglobin, which gives us our greatest quantity, and then there's the freely dissolved oxygen, which is a much smaller quantity, but the dissolved oxygen contributes to that partial pressure. The CO2 transport is different. Okay, so carbon dioxide is transported 90%. Is converted to something called carbonic acid and bicarb, a bicarb ion. So I'll draw that equation in just a minute. 5% is going to be bound to proteins like hemoglobin, so it can bind to hemoglobin. It binds at a different site than oxygen, though. And then 5% can be dissolved directly in the plasma. Okay, so 5% directly dissolved. So when we have sort of exchange occurring at the lungs, most of the CO2, you don't have to remember these exact percentages, but most of the CO2 is going to come from the carbonic acid, that 90% that's been converted, is going to be converted back into CO2. Okay, the next biggest is going to be being released from hemoglobin, for example, and then the least is going to be coming from the plasma. Now, the relationship of CO2 to carbonic acid, this is a formula that you guys may have seen in biochem already. If not, this is one you're going to have to memorize. So we're going to be using this a lot. So CO2 plus water. CO2 plus water gives us H2CO3. Now, this is a reversible reaction. Okay, so this right here is carbonic acid. So CO2 combines with water, and it requires an enzyme. The enzyme I'm going to show you on the next slides, carbonic anhydrase. I'm just going to put Ca there. Carbonic anhydrase. This is a reversible reaction. Now the other half of this formula, which is also reversible, carbonic acid dissociates into HCO3 minus plus a proton or hydrogen ion. So this formula we need to memorize because this one is how the lungs help to regulate our acid-base balance. And you can see acid-base because if we're dealing with protons at all, that can affect, the concentration of protons affects the pH. And bicarb would be acting here as a buffer. So what we have is CO2 combines with water in the presence of our enzyme carbonic anhydrase that catalyzes the action of that to become carbonic acid, which dissociates into bicarb and hydrogen ion. And this is reversible. So we can go from, the hydrogen ions can combine with bicarb to form CO2 and water. So in other words, at the tissue level, when we're producing the CO2, 90% of that CO2 that's being produced is going to combine with water in the presence of carbonic anhydrase, and it's going to become bicarb and a proton here. The rest, some of that CO2, the 5% is going to go to hemoglobin, and the other 5% is going to go directly into the plasma. Now here, this graph again, you can see the bottom portion down here, this particularly looks familiar. That's the sigmoid curve, the hemoglobin dissociation curve, all right, for oxygen. All right, and you can see down here is the physically dissolved oxygen. So that's what we've already talked about. And this is the relative concentrations or the quantity, again, mils per deciliter. But this is adding the CO2 components to see how CO2 compares. And you'll notice that the physically dissolved CO2, it's also linear. And so as the partial pressures of CO2 go up, it dissolves more readily than the oxygen. And again, I mentioned this earlier, CO2 is more soluble. So even for the same partial pressure, you'd get a lot more CO2 dissolved than you would oxygen. Now here, you can see that, for example, the partial pressure of CO2 is 100. You'd have much more CO2 dissolved relative to, say, the O2. Now over here, this is the total blood CO2. So just as the hemoglobin plus the dissolved oxygen make up the total amount of oxygen in our blood, we have the dissolved CO2 component now plus the what's been converted to bicarb and bound to proteins and so on. But you'll notice the shape of the curve is different. It doesn't follow the same hemoglobin dissociation curve because we're not really, it doesn't have the same properties, okay? Because even though some CO2 binds to hemoglobin, it doesn't bind at the same site. It doesn't bind at the heme group. So you'll notice that here's the artery and the venous portion. So if we're talking about total CO2 at a partial pressure of about 40, which is our arterial partial pressure of CO2, that coincides with a quantity of CO2 of about 50 mLs per deciliter. And remember that on the venous side, the CO2 only goes up by about 6 millimeters of mercury. All right, so the venous side there. So you're looking at a quantity of maybe 55 mils per deciliter. So we're working within a much narrower range compared to the oxygen because our partial pressures, physiologically speaking, are from 40 to 46. So it's a much narrower range. And those are the quantities we're talking about. And so you'll notice that in that physiological range, we don't have a sigmoid relationship within that range. It's really a linear relationship. So this is actually an important feature when we start talking about ventilation perfusion mismatches and so on. So we'll come back to that. Okay, so here's our systemic gas exchange. So this is the gas exchange occurring at the tissue. All right. So you can see on the right side, you see our red blood cell. On the left side, we have our metabolizing tissue. All right, it's showing you, the interstitial tissue there. All right, it's not really showing you the cells there. Now, in terms of the CO2, remember the tissues are producing CO2 as they're metabolizing. Some of it's going to be directly dissolved, so you see a smaller arrow there because it's only like 5%. Another 5% of the CO2 is going to bind to proteins. Some of it's going to be some of the plasma protein, but the majority of the CO2 that binds to protein would be hemoglobin. So you have hemoglobin CO2. And again, it's binding to the globin portion. It's not binding to the heme, so it doesn't follow the same rules. Finally, the biggest portion of CO2, or 90% of that, which is the large arrow here, is CO2 that when it dissolves, it's actually going to go into the red blood cell because the red blood cells contain carbonic anhydrase, which is the enzyme that catalyzes this reaction. And so the CO2 combines with water, becomes carbonic acid. This is what I drew for you earlier. And then that dissociates into bicarb and a hydrogen ion. Now on the membrane of the red blood cell, there is a receptor there that exchanges bicarb for chloride. So what happens is as the bicarb levels start to go up, because we have all the CO2 that's diffusing into the red blood cell, we're going to accumulate lots of bicarb and protons. Now, the bicarb actually gets shifted into the blood via this channel in exchange for chloride. So we're basically exchanging anions. There's an anion exchange here. All right, so we have something called a chloride shift because we're moving chloride from inside the plasma and moving it into the red blood cell in exchange for bicarb. So the chloride moves in, all right, bicarb leaves, and the proton that's accumulating, now that would normally, if it was free protons, that would decrease the pH of the red blood cell significantly and become very acidic. But instead, the proton here is going to combine with the oxyhemoglobin. So it has a very high affinity for oxyhemoglobin, so when it binds to it, it actually lowers the affinity for oxygen once it binds. So that's the proton binding to the hemoglobin, and its binding to the hemoglobin reduces the affinity for oxygen. And so then oxygen is shifted off the hemoglobin, right? Now what I would change about this graph is the oxygen is shifted off the hemoglobin, would go directly into the plasma and become dissolved O2, and then move from dissolved into the tissue, based on what we talked about from the previous slide. So I'll say that one more time. Okay, most of the CO2, 90%, is going to go through our pathway here to produce bicarb and a proton. Bicarb gets shifted into the plasma in exchange for chloride, and the proton binds to the hemoglobin, lowers the affinity for oxygen. Oxygen then leaves the hemoglobin, goes into the plasma into a dissolved state, and then goes down its partial pressure gradient from there. Now, in the alveoli, we're going to have essentially the reverse reaction. So on the left, you see the alveolar airspace, and then on the right, you see the capillary in our red blood cell. Okay, so remember, there's a high concentration of, or high partial pressure of oxygen on the left here. So oxygen is moving into the plasma. So again, what I would change about this particular cartoon is that the oxygen is going into a dissolved state first. Okay, so it's not really depicting that in this cartoon. So it dissolves first, and then from the dissolved state, it then binds to oxygen. Then binds to hemoglobin. Diffuses, across the membrane and binds to the hemoglobin. At a high enough partial pressure, that actually helps to reverse the reaction. So when oxygen binds to hemoglobin, it dissociates with the proton here. This is still within the red blood cell. It's dissociating from the proton. All right, that's going to increase the free proton there. This membrane on the surface of the red blood cell is going to have a reverse exchange occur. Bicarb is now going to move into the cell, and chloride is going to shift out. So chloride, now they're doing an exchange again. So as the bicarb moves in, it's going to combine with that proton that just got released from hemoglobin, and that's going to reverse our reaction back into a carbonic acid, back into CO2 and water, and the CO2 is then going to leave and go into the alveoli, and that's going to be the primary way in which we can get rid of CO2. Some of the hemoglobin that's bound to CO2 will also dissociate. All right, and then some of the directly dissolved CO2 will move out of the capillary blood and into the alveoli. So the main way in which the CO2 is coming from is from this pathway inside the red blood cell. All right, the way we reverse that reaction is because oxygen at high enough partial pressures, a high enough quantity, will actually bind to the hemoglobin, release that proton. The affinity for hemoglobin for oxygen will go up and we'll release more and more protons, so that's going to start to accumulate in the red blood cell. I get a reverse shift, so bicarb starts moving into the red blood cell. Protons and bicarbs come together. The CO2 then that's produced from that reverse reaction will get released. Okay, just briefly, I want to just touch on cyanosis real quick, give us a little bit of a clinical correlate. Cyanosis, which is that bluish discoloration you see in the lips or the tongue or on the fingertips or the toes, there are multiple underlying causes that can elicit that sort of phenotype, and we'll get more into that in the cardiology lectures. But just to give you an idea is that to have cyanosis, the arterial blood itself, so the arterial blood that's going to those capillaries of the lips and of the fingertips, it has to be deoxygenated by about 5 grams per deciliter. In other words, if you have a normal 15 grams per deciliter of hemoglobin, if a third of that, approximately, right, about 5, so if a third of that is deoxygenated, meaning it's not saturating, we're not saturated, and that's in your arterial system, then you can see bluish discoloration of the lips and the tongue and so on. And there are many ways that this can happen. It can happen distally in the extremity from vasoconstriction. It can happen from pulmonary conditions. It can happen from heart conditions, and we'll kind of touch on that later on. But ultimately, it's because you have a desaturation of your hemoglobin in the arterial system. So when it's feeding those capillary beds, it's showing up kind of bluish. And so you're kind of seeing that over here, that if this is our oxyhemoglobin dissociation curve, if I have instead of 15 grams per deciliter, it's now 10 grams per deciliter that's carrying oxygen and 5 or not. That's going to drop the total content of oxygen I have in my arterial system, and that can be, instead of being 20, it might be down around like 12 or 13 milliliters per deciliter of oxygen. So the quantity in my arterial system has gone down significantly, and so that's going to be a drop in my saturation, and that's going to show as cyanosis. This differs from pallor, in that pallor, it's not a deoxygenation of hemoglobin per se, but a drop in total number of red blood cells. So they do differ a little bit, and again, we'll come back to that more in the lectures to come. So in terms of control of our respiration, all right, so now we're kind of backing out a little bit. We talked about the exchange and how we transport it, but in general, we've talked about tidal volumes and different volumes that we have. We know that it's automated. We can just breathe automatically without thinking about it, but then when we start thinking about it, we can kind of override those responses. So there's multiple portions of our brain that contribute to the regulation of our respiratory system. So first off, at rest, it's automatic. It can be unconscious cycle of breathing. And so this is primarily carried out by these respiratory centers that are located in the brainstem, the medulla oblongata, and the pons. So in the medulla, we actually have an area called the dorsal respiratory group and the ventral respiratory group, because of the locations of where they are in the brainstem. Now, the dorsal respiratory group is considered primarily the active one while we're resting, because that's driving inspiration, which means it has to activate things like our intercostal muscles and our diaphragm so that we can decrease the pressures intrathoracically and drive air in. So it has to work, and we know that our respiratory rate on average is approximately about 12 breaths per minute. So this is firing, this DRG is firing about at a rate about 12 per minute, which then activates those intercostals and diaphragms to promote the inspiration. The ventral respiratory group works during expiration. So it's not typically on during unconscious breathing, because we don't use muscles. We don't have to activate muscles to exhale. So it's a passive process. So the VRG is not usually active during resting breathing. However, if we want to forcefully exhale, the VRG would then come into play. Then it's going to activate the muscles that are required for forceful expiration. And then lastly, we do have a reflex called the Herringbauer reflex, which is a stretch reflex, and it's located in some of the airways of our lungs. And what that does is it essentially helps to signal the brain when we're breathing in to not overinflate the lungs, because we don't want to overinflate them and cause damage. So it's a signal that goes back to the brain and tells it to inhibit the inspiratory effort. The pons. So again, now the medulla is pretty much carrying out the quiet respiration. Inspiration is primarily the DRG that's active. The pons, on the other hand, modifies the rhythm based on the circumstance. So if we're sleeping, it's going to adjust the rhythm with which we breathe. If we're exercising, we breathe differently, right? If we're vocalizing, as I'm talking to you, I have to change the pattern with which I breathe. If you're singing, if you're having an emotional response, the pons then communicates with the dorsal or the DRG and the VRG to coordinate how the breathing patterns have to take place in order to carry out that particular function. So it's a modifier. And then the cortex, of course, if we go a little bit higher into the cortex, we have voluntary control of breathing, which means we can think about breathing. I want to breathe in deep now, right? So I was signaling from the cortex to the brainstem, telling it to take a deep breath in, or forcefully exhale. So telling the VRG to activate and forcefully exhale. So there are controls that we have that can voluntarily override. And yet down here in the cartoon, you can see the pons, just as a reminder. This is in the brainstem, so that's the pons region, and the medulla just inferior to that. So now, in order to regulate the respiratory rate and rhythm appropriately for a given situation, we don't always want to have to think about it voluntarily. Like if we're exercising, okay, I need to increase my respiratory rate and the depth with which I breathe. We're going to need what we call central and peripheral input centers that help signal the respiratory centers in the brainstem to adjust accordingly. So for example, and these are, by the way, things I have mentioned already in the cardiovascular lecture, the central chemoreceptors. All right, these are brainstem neurons that respond to changes in primarily the pH. So changes in that proton concentration. So as the proton concentration goes up, the pH goes down. And that actually signals an increase in the respiratory rate. So again, that increase in protons is going to increase our respiratory drive. Now, the reality is this, that drop in pH in the cerebral spinal fluid is the fluid that surrounds the brainstem there, and it's going to interact with these specialized central chemoreceptors. That's actually an indirect reflection of the CO2 level in our blood. Okay, and so what happens is the CO2 level will start to rise, and let's say the CO2 level starts to rise in the peripheral blood. What happens is the CO2 will then diffuse readily across the blood-brain barrier into the cerebral spinal fluid and then be converted into protons because there's carbonic anhydrase in those cells there. So again, this is the CO2 plus water. We're going to yield H2CO3, bicarb plus the hydrogen ion. So there's our CO2 and there's our proton. So what you're seeing is that as the CO2 levels start to rise, that actually diffuses across our blood-brain barrier into the cerebral spinal fluid, and these specialized central chemoreceptors can convert that to protons. They can be converted to protons. As that proton level starts to rise, which is a decrease in our pH, that's going to stimulate respiratory centers to increase respiratory rate. In other words, blow off that CO2, get rid of the CO2 that's over here. We want to decrease that CO2 by breathing it off, and that's going to shift everything in this direction, so the pH renormalizes. All right, and this is our primary regulator of respiration. Now, the peripheral chemoreceptors do play a role as well. The peripheral chemoreceptors are located in the carotid and aortic bodies. So, right near the aortic bifurcation, all right, the carotid bifurcation and in the arch of the aorta, similar to what we talked about, right, in the cardiovascular lecture. So that should seem familiar. They respond to oxygen, CO2, and pH, which is exactly what the lungs are supposed to regulate, so it's good that we're sensing for them. So if there's a low level of oxygen, it'll increase respiratory rate. If there's a high level of CO2, it increases respiratory rate. And if the pH drops, it increases respiratory rate. And so oxygen, however, is not the primary driver of respiration under normal circumstances. It doesn't trigger until we're very hypoxic, usually less than about 60 millimeters of mercury or so. So the primary driver under normal physiological conditions, of healthy adults, is going to be CO2, because CO2 can directly stimulate the peripheral chemoreceptors, but centrally, it's going to be converted into protons, which will stimulate the central ones. So to stimulate an increase in my respiratory rate or my breathing, if we're talking about the central receptors, again, located in that brainstem there, it's responding primarily to a drop in the pH or to acidity. And so again, just a reminder, that's an increase in the number of protons. That's an up arrow. Sorry, it's not a very good one. All right, so it's an increase in protons. This is due to an increase in the CO2 that's occurring in the rest of the body, because what happens is the CO2 accumulates, it crosses the blood-brain barrier very readily, and enters into the cerebral spinal fluid, gets converted into bicarb and the proton based on that formula I showed you guys, one that, again, you guys need to know. So this is an indirect relation to the increasing CO2. And so you can imagine logically, if the CO2 is going up, when I breathe faster, right, and I breathe more deeply, I can get rid of more CO2, right? So I would increase what we call my ventilation rate. By ventilating more, I get rid of the excess CO2, and that's what happens centrally. As the pH drops because of an elevated CO2 peripherally, then I'm going to increase my breathing rate, and the reverse would be true. If the CO2 is dropping, then my pH would go up centrally, and that would slow down my ventilation. So this is how we can maintain CO2 levels. Peripherally, okay, they do play a role. So we do have the carotid and the aortic bodies. And so they do respond to O2 directly, but like I said before, that really doesn't play a major role under standard physiologic conditions unless the PO2 drops significantly, like less than 60 millimeters of mercury, so like very, very high altitudes and whatnot. And I'll give an example of that in the next lecture. It does respond to CO2 directly, and it does respond to hydrogen ions directly. So, and it follows the same pattern. So if oxygen is low, obviously I want to increase my respiratory rate to bring in more oxygen, breathe in more. right? And when I breathe in, as I increase my ventilation, I'm bringing in more oxygen, and I'm also getting rid of CO2, so it works both ways. So the CO2, if it's increased, I would increase my ventilation. And if my pH is low, okay, if I'm acidic, I would also increase my ventilation. And again, that's due to the relationship between CO2 and hydrogen ions. So something we're going to be talking quite a bit about in some of the lectures to come, particularly the renal lectures, are what we call blood gases. So this is, something referred to as like an ABG, for example, an arterial blood gas. And we can actually measure partial pressures, and we can measure things like bicarb levels and so on. And it's very, very useful for many conditions, oftentimes that you would see in an emergency room or in an ICU. So the rate and the depth of breathing can be adjusted to maintain those levels we just talked about. So those, the brainstem, as well in its interaction with the central and peripheral chemoreceptors, help to adjust the rate, not only the rate, but also the depth with which we breathe. Okay, and in this way we can regulate and maintain the pH by adjusting the CO2 levels. Okay, and it helps to also adjust the oxygen at the same time. So, for example, the pH in our blood. So these are some numbers you will need to know. The pH of our blood is typically about 7.4. There's a range, about 7.35 to 7.45. I'm going to be generally just using 7.4. Okay, so that's the pH. The PaCO2, all right, so the partial pressure of CO2 in the arteries is 40 millimeters of mercury. We knew that because we talked about that in the beginning of this lecture. The partial pressure of oxygen in the arteries should be about 95. Again, what we talked about from earlier in the lecture. But we can measure that directly. And so what we're going to do is talk about later on how changes in respiratory rate can affect CO2 and oxygen levels and how that can adjust for the pH. Because maintaining that pH is of vital importance to the function of so many of our systems. Because if the pH changes too drastically, it changes binding properties, it can cause dissociation of proteins and so on. So it can be quite devastating. So maintaining that is important. And knowing that CO2 plays a role in that, because CO2 is in balance and in equilibrium with bicarb and a proton, means that if we regulate CO2, we can also regulate proton content. So we'll come back to that. So the most potent stimulus for breathing is going to be the proton, because the central chemoreceptors are more potent. Okay, and that's what they respond to, which is again indirectly because of the CO2 level. All right, and then the O2 is only found in the peripheral chemoreceptors, but they'll come more into play in severely hypoxic states or at very high altitudes, and we'll talk about that in certain disease states. So you guys are going to need to remember again that CO2 plus water is in a reversible reaction to form carbonic acid, H2CO3, which then forms bicarb plus a proton. This relationship is of vital importance, so we need to remember this, and it's reversible and requires that enzyme carbonic anhydrase. Okay, so again, this proton over here is going to relate to the pH and how that gets regulated, and the CO2 over here is something that we can actually regulate by breathing, changing the rate and depth with which we breathe. So now to finish up, I just want to talk about the blood-brain barrier and its relationship with that equation. So remember that CO2, okay, when it accumulates peripherally, that triggers the central chemoreceptors to increase the respiratory rate. And it does so because the CO2 gets converted into bicarb and proton. So what you're seeing here is if this is the cerebral spinal fluid, and there's the brain, where the central receptors would be located somewhere over here in the brainstem. You notice that CO2, this is from the body, is crossing the blood-brain barrier. That's what the BBB is right there. It crosses very readily. All right, it's very soluble across that membrane, so it gets over there very easily. And you'll notice that there is carbonic anhydrase, and so it can be converted into ultimately bicarb and a proton. So again, if CO2 accumulates, it crosses there, and we get an increase. That's going to stimulate our respiratory rate. The point I'm trying to make with this particular slide is that CO2 quickly equilibrates from the peripheral arteries across that blood-brain barrier and into the CSF. It moves very readily. So that exchange occurs very rapidly, whereas the proton and the bicarb ions. That exchange can still happen again peripherally, because we talked about that. We can still convert CO2 into bicarb proton in the peripheral circulation. These are charged though. Proton has a positive charge, the bicarb has a negative charge, and because they're charged, they don't readily cross the blood-brain barrier. They still will, but it takes a lot longer. So what you're seeing is that little squiggly arrow there to show that this is not crossing the membrane as readily here. So it's slower to equilibrate across the blood-brain barrier, is my point. This feature of CO2 moving quickly, but the protons and the bicarb don't do it as readily, becomes of clinical importance, and in terms of treatment becomes important. And I'm going to give some examples in the Zoom lecture to go over that more specifically. Okay? But just to give you one quick review. Okay, so to wrap this up, this is the same cartoon that we saw on the previous slide. This is just giving you a quick example of how some of this compensation works. And we'll get into more depth on this and maybe some other examples in the Zoom session. So again, we have to remember that formula, how CO2 can be converted into bicarb and a proton, and that there's a balancing act in maintaining CO2 levels and our proton levels so that we can maintain our pH and our CO2 levels appropriately. So in this example, this is somebody who has insulin deficiency because, let's say, they have some form of diabetes. So the pancreas isn't producing insulin, and in response to that, the liver starts producing ketones. It undergoes what we call ketosis. Now, these ketones, they're acidic. So it's actually increasing the acidity of the blood, because as the demand for nutrition goes up and the insulin is deficient, it starts to rely heavily on these ketones. And so the liver starts to produce more and more of them. And so the proton level starts to go up and up and up. And as the proton concentration goes up, the pH goes down, becomes more acidic. Okay. Now, if you recall, our peripheral chemoreceptors are responsive to the change in the proton, as well as our central receptors, chemoreceptors. But keep in mind what I said on the previous slide, is that protons, they're positively charged, and if they're accumulating peripherally, they don't readily cross the blood-brain barrier. So it takes a long time for them to actually cross into the cerebral spinal fluid to cause any kind of change, whereas CO2 could cross very readily. So we'll keep that in mind. So the protons are accumulating peripherally, not crossing the blood-brain barrier just yet, so they can activate the peripheral chemoreceptors. And so you see that there, it's stimulating the chemoreceptors that are located peripherally, again in the aorta or the carotids. And it stimulates them. And when it stimulates them, that increase in hydrogen ion, really, concentration, that's going to stimulate them, and that's going to stimulate the respiratory centers in the brain. And in response to that, that's going to increase our respiration in the lungs. So it's going to increase the rate and the depth with which we breathe. And the effect of that is, by increasing our ventilation overall, is to bring in more oxygen, but more importantly, in terms of our acidity, it's going to decrease the CO2 because we're going to breathe off that CO2. Remember, that's the relationship with CO2 and the bicarb there. It's a reversible reaction. So it's going to drop the CO2 because I'm breathing more rapidly and deeper. So somebody who's in ketosis due to their diabetes, you'd see them breathing more rapidly and deeper to drop the CO2. What benefit is it to have the CO2 drop? Well, if the CO2 drops, since it's in a reversible reaction with the bicarb and the proton, what's going to happen is it's going to shift the equation to the left there. In other words, as the CO2 drops, since they're in an equilibrium, if one side starts to drop, the other side shifts towards it. So the proton and the bicarb will combine and produce more CO2. The ultimate effect of that is by dropping the CO2 and causing that shift where bicarb and proton combine and then convert into CO2, is that drops the free proton concentration, which helps bring my pH up. So that's a compensation for. So when you see somebody breathing deeply like that, this is a respiratory compensation for the acidity caused by the keto acids being produced by the liver. All right? And as I mentioned earlier, the protons that have been accumulating because of this ketosis, they don't readily cross the blood-brain barrier, but the change in CO2 does take effect. So what ends up happening is the CO2 crosses readily. The CSF, remember, it has the same equation here because it also has carbonic anhydrase. So its CO2 level will actually drop slightly because the CO2 will go down its partial pressure gradient. So as CO2 drops peripherally, it'll also leave the cerebral spinal fluid there. And since the protons really haven't crossed over much yet, what ends up happening if I just drop the CO2, it's still going to cause the equation to shift towards the left. So bicarbs are going to combine with proteins. But in the CSF, since I don't have an elevation in the protons just yet, a drop in my CO2 causes a drop in my proton concentration. And my proton concentration isn't high in my CSF yet. So what ends up happening is I can actually increase my pH slightly. So that's what you're seeing at step 9 down here. The CSF is not yet acidic because the protons haven't really readily crossed yet. So it could be even slightly alkaline. And the reason is because the CO2 level is dropped because we're breathing off some of that CO2. And it equilibrates across that blood-brain barrier very rapidly. So this is sort of a complex situation, but you can see that, again, this is to allude towards the fact that the respiratory system can compensate for changes in our pH, because ultimately that's what it's regulating, is oxygen, CO2, and the proton concentration. We haven't talked about the kidneys yet, but when we talk about that, we'll talk about the combination of both the kidneys and the respiratory system and how they work together to maintain the pH, the CO2, and the O2 together. Okay, and in the Zoom, I will go over some more examples with this. Okay, all right, guys, we'll see you then.